Welcome to Daily Papers, the podcast where we break down the latest academic research and what it means for you.
Today, we're diving into the world of cybersecurity, a world that often feels like a high-stakes, never-ending game of cat and mouse between attackers and defenders.
Exactly. Hackers are constantly creating new malicious software, or malware, and security experts are always trying to find new ways to detect and block it. The problem is, as soon as a new defense is built, attackers start figuring out a way around it.
Which brings us to today's paper from researchers at the University of California, Berkeley. It's called Trident, Improving Malware Detection with LLMs and Behavioral Features. And it proposes a really clever new way to use AI to get a step ahead in this arms race.
So before we get to Trident, let's quickly talk about how we traditionally find malware. There are two main approaches: static analysis and dynamic analysis.
Static analysis is like reading the blueprint of a software program without actually running it. You look at the raw code, the text strings inside it, the file size, all the things you can see just by looking at the file itself.
The advantage is that it's fast and safe because you never actually run the potentially dangerous code. The big disadvantage is that malware creators know this, and they've gotten very good at disguising their code. They can pack it, encrypt it, and make it look completely harmless on the surface.
So that brings us to the other method, dynamic analysis. This is where you take a suspicious file and run it in a safe, isolated environment called a sandbox. It's like letting a wild animal loose in a secure enclosure so you can watch what it does.
You're watching its behavior. Does it try to delete your personal files? Does it try to modify critical system settings? Does it try to connect to a suspicious server on the internet? These behaviors are much harder for malware to fake.
But this method has its own problems. For one, it's slower, and some really clever malware can actually detect when it's inside a sandbox. It knows it's being watched, so it just sits there and does nothing, waiting until it gets on a real user's computer to activate.
And both of these methods suffer from a huge problem that the paper focuses on, called concept drift.
Concept drift is a great term. The simplest way to explain it is that malware is like fashion. The styles are constantly changing. A machine learning model that you trained a year ago to spot last year's malware might be completely clueless when it sees the new styles of malware that are popular today.
This means that over time, the performance of these detection models gets worse and worse. They start missing more and more new threats. The typical solution is to constantly retrain the model with new data, which is expensive and time-consuming.
And this is where the Berkeley researchers bring in a new tool, large language models, or LLMs. These are the powerful AI systems behind things like ChatGPT.
Instead of just using a traditional model, they decided to let an LLM read the reports generated by the dynamic analysis sandbox. They basically showed an LLM a report of a known piece of malware and asked it, "Hey, you're a smart security analyst. What's the suspicious behavior here?"
And the LLM is incredibly good at this. It can read through a messy technical log file and pick out the key malicious actions. For example, it might say, this program is writing to a specific system file called app_init_dlls. This is a well-known technique malware uses to make sure it runs every time the computer starts.
But here's the really cool part. They didn't just ask the LLM to spot the bad behavior, they asked it to write a simple, automated rule to detect that specific behavior in the future. So the LLM would generate a rule that basically says, from now on, if you see any program trying to modify that app_init_dlls file, flag it as suspicious.
This is a huge step. These rules are based on fundamental malicious behaviors, which change much slower than the surface-level features that static analysis looks at. Plus, the rules are easy for a human to read and understand.
Now, LLMs can sometimes be a little overeager. They might write a rule that sounds good but ends up flagging legitimate software too. This is what we call a false positive, and you really want to avoid those. You don't want your antivirus blocking Microsoft Word.
So, the researchers added a crucial validation step. They tested every single rule the LLM created against a big data set of known, perfectly safe software. If a rule ever flagged a safe program, they just threw that rule away. This let them build a high-quality set of rules that were great at catching bad behavior without flagging good behavior.
So now they have two different systems, the old, fast but brittle, and static analysis, and the new, robust behavioral rules created by the LLM. The final step was to combine them along with the LLM itself into one super detector they named Trident.
Trident works like a panel of 3 judges. When a new unknown file comes along, it's judged by all 3. Judge number 1 is the traditional static model. Judge number 2 is the set of behavioral rules, and judge number 3 is the LLM, which gets to look at the sandbox report directly and give its own opinion.
Then they just take a majority vote. If 2 or more of the 3 say the file is malware, it gets blocked. This hybrid approach is the key. It uses the strengths of each method to cover the weaknesses of the others.
And the results were fantastic. Trident performed better than any of the individual methods on their own, but the most important finding was its resilience to concept drift.
Right. While the traditional static model's accuracy dropped significantly over the course of a year, Trident's performance stayed incredibly high and stable. It was able to keep catching new and evolving malware families that it had never seen before.
And it achieved this without needing constant, expensive retraining. By focusing on fundamental behaviors, it built a system that doesn't just memorize what old malware looks like, but understands what it means for software to act maliciously. It's a huge leap forward in making our digital world a little bit safer.